All right, well, thank you. This is just a little bit of research that several folks at the Storm Prediction Center, including Rich Thompson, Andy Dean, Chris Karstens, and Doug Spieger next door at the Norman Forecast Office have been working on the last couple of years. And so we're going to focus, this database that I'm going to discuss is a tornado-only data set, but we've uncovered some pretty interesting findings with it. So what this data set, we went back and investigated all of the damage survey points from 2009 through 2016 that were a part of the digital data set referred to as the Damage Assessment Toolkit, or for short, the DAT. And we matched these damage survey points up to the nearest circulations responsible to them from single site 88D imagery, and from this we took the nearest DIs to the circulations and assigned the peak damage indicator wind speed from those possible DIs. So on the far left of the screen you can see 6 different upside down triangles. Those were associated with the circulation as it moved from left to right. This was the EF4 Perrysville, Missouri, into the Illinois tornado back in February 2017, I believe. And so the peak damage indicator for the leftmost volume scan, sampling from Paducah's radar, was 180 miles an hour with that scan. And we did this for about 2,500 different tornadoes that were included in the DAT, and out of like about a possible 35,000 different damage indicators. So it's a pretty extensive data set. And so with the radar imagery, I do want to make a point that the radar interrogation, we made a pretty careful consideration in terms of what velocities to choose, and which we used like a threshold of reflectivity of roughly 20 or so dBz, as well as a high correlation coefficient to signify that we're actually sampling meteorological scatterers versus maybe side lobe type contamination. So we took pretty careful care with that. And that's a must in terms of if you were to use this in practice. So I guess next slide, if I'm able to advance here. So with different geographic areas, you're going to get different damage wind speeds associated with, say, an equal strength tornado. So if you're in western Kansas, a lot of the times you're going to, if you have a very intense tornado, you're only going to reveal weak to maybe moderate type tornado damage occasionally because you just aren't hitting much. Whereas if you're in a higher populated area, say the suburbs to Chicago, you're going to tend to reveal that type of damage much more so. So this is a chart right here in which we took all of these damage indicator scans or points with all these different tornado events across the CONUS and parsed them into an environment based on the significant tornado parameter, taking a maximum value within 80 kilometers, and also the rotational velocity, or VROC for short. And from that, we then matched these different kind of factors together. And so for this, the bottom one, we kind of broke this into 5 different categories or levels. So all of the events that were less than 1 STP and less than 30 knots rotational velocity, those damage indicators, 96% of those that had those 2 criteria had wind speeds between 60 and 110 miles an hour. So 24 out of 25 scans in which you have that criteria, you're going to get a wind speed between 60 and 110, at least in terms of what is surveyed. If you have a little bit more volatile environment, say an STP of 3 or higher, and a rotational velocity between 50 and 80 knots, which is what you would find with a pretty intense supercell tornado, 72% of the time, you're going to have a wind speed between 100 miles an hour and 175 miles an hour. Again, this is based solely on a on a tornado-only data set, but it's pretty tightly matched in time and space to radar scans. So, and then finally up on the top, in the level 4, looking at STP of 4 and greater and 70 knots and greater, tend to find those types of events more than, or around 3/4 of them, ranging between 120 and 210 miles an hour. And so we also had, I have a GIS background and compared population density in terms of being able to compare events that would have, say, a high STP of 4 and higher and 70 knot greater VROT, and those events that are ones in which that tend to occur in a population footprint of 20 people per more, or 20 people or more per square kilometer, tend to reveal a higher damage intensity. And 20 persons per square kilometer was actually based on a study that looked at the top 50 U.S. cities, looking at the exurbia population for those top 50 U.S. cities, and the lowest exurbia population threshold was 24 people per square kilometer, and that was Minneapolis-St. Paul. All of the other cities in the U.S., the big cities, have a higher, lower threshold for an exurbia population. So this is just when you're starting to get into more meaningful structures or density of structures. So with the next slide, I'm going to show how this kind of compares in terms of the box and whisker distribution, looking at the 10th to the 25th, 50th, which is the median value, and that's signified by the circles on these horizontal box and whisker distributions, the 75th percentile, the rightmost part of the box, and then the rightmost whisker is the 90th percentile. So on the x-axis, we have the damage indicator wind speed increasing from left to right, and then on the y-axis, the rotational velocity going increasing. And so you can see how these different levels, again, just looking at combinations of STP and rotational velocity time matched to these different tornado events, you can see how with a higher rotational velocity tends to correspond to a higher damage indicator wind speed. And I've also annotated on there the median value of the significant tornado parameter maximum value within 80 kilometers or 50 miles. And you can see those distributions. So I just mentioned a little bit about the population density and how that tends to provide an ability to reveal higher wind speeds with damage. And you have these pretty good environments of 4 STP and higher and 70 knot or greater VROT. And we tested those based on an exceedance value of population density. If you just have anything in terms of a population density, that's the level 4 distribution that you can see. If you exclude values less than 5, or 5 and higher, excuse me, the median value starts to shift to the right, 10, 15, and 20. So you can see how the median value, just by including population density, tends to shift that damage intensity to the right. So on the next slide, we're just going to look at a couple of examples, the most recent significant tornadoes that have impacted the lower 48. So this EF3 that impacted Columbus, Mississippi here back in February. It was an STP value between 2 and 3. So we would look at on this chart that would not fall within that level 3 of being greater than 3. So we had dropped down to this level 2 value greater than 1. just to look at it from an environment, kind of setting the table. On the next slide, we're looking at a graph of the rotational velocity, and I've also annotated on this time series the performance in terms of what was issued by the Memphis, Tennessee office. So the rotational velocity began with the tornado around 40 knot rotational velocity. It increased above 50 knots and then started to just gradually weaken during this 15-minute tornado. So those values of rotational velocity tended to fall in this range of, say, 25 to 65 knots. And so we would expect damage at the surface in terms of the peak damage indicator wind speed between 80 and 140 miles an hour, at least 81% of the time in terms of a scan perspective. So looking at how this verified, 9 out of the 10 scans, we had a peak damage indicator wind speeds between 80 and 140. It peaked at 137 miles an hour, and then the last scan fell just below 80 miles an hour. I think it was like 77. So the most recent intense tornado that we've had on the next slide, we can look at the Alabama, Beauregard, into Georgia event, and the STP of between, say, 3 and 4 in proximity to that event puts you in this kind of level 3 category. On the next slide, we can look at the rotational velocity time series, and also, of course, annotated is the how the Birmingham and Peachtree City offices handled this event in terms of SVS statements. And the rotational velocity increased dramatically near the start of the tornado when we started getting a TDS signature right away. On the following slide, we're looking at the damage indicator wind speeds, the peak DI wind speed values, and notice there tends to be a pretty strong ramp up in the DI wind speeds that tended to correspond to the market increase in rotational velocity. And also on there, we have kind of some missing values in terms of DI wind speeds per each volume scan, and those just were not, if there was damage along the path, it just wasn't perhaps included in the DAT when I did this graphic a couple of weeks ago. But so in terms of how this verified, 7 out of 9 scans when you had a VROT between, say, 25 and 65 knots, again, you would have been above a 1 STP. 7 out of those 9 scans fit that criteria. But when you were above 50 knots, 50 to 80 knots, 16 out of 17 scans revealed damage between 100 and 175. So it actually performed pretty well for this event. So on the following slide, just to kind of here wrap up, we've also included a table that basically accounts for all possibilities and how events would be handled. Maybe if you wanted to use this as a SVS, decision support type tool. And so over there on the right is how those scans kind of verified. And my email address is there on the bottom. And just a little plug in terms of what we're doing at the hazardous weather test bed this coming spring. On the last slide here, we've worked with NSSL, Bryan Smith and Matt Mihalik, and we've now got some gridded output from MRMS data that's going to be looked at based on this DAT data set. And instead of looking at VROT, manually calculating it, it's taking the ASHEAR algorithm available and assigning probabilities based on different thresholds. So in this particular example, we're looking at what's the probability of getting at least 170 plus mile an hour for this particular scan, and this was the 2006Z scan just east of Maxwell Air Force Base, and it's based on a logistic regression model, and we tended to get a pretty high value, so this was kind of a promising result that was certainly going to be looked at more in depth here coming up this spring. So I guess I'll go ahead and stop and take any questions that you may have. Thanks.
Thanks, Bryan. That's really exciting work. I see a lot of synergy there between the presentation that Aaron and John had on looking at radar signatures in association with the work that you just presented here on then when you make that tornado warning decision that you can message it in a way based on some of the work that you've done. Do you have any recommendations, any questions from the field, first of all? Anybody want to raise their hand, and I'll unmute you for a question. While we're waiting, Bryan, what do you have any recommendations for messaging, or is it mainly something that you would just utilize in the warning itself?
I think with this being a diagnostic, I think the SVS is probably the most appropriate type tool, although from a tornado warning standpoint, so I'm referring to the IBW tags, the considerable and catastrophic or just the base tier, but from a tornado warning standpoint, you can certainly utilize rotational velocity to anticipate thresholds. In terms of our database, we have not found really anything above the 60 knot rotational velocity that is not tornadic, and this is looking at thousands of tornadoes. So when we tend to get those higher rotational velocities, that's telling you something in terms of what's going on at the ground.
Outstanding. Thanks again, Bryan.